will help you identify all the possible outcomes of an event is called the systematic listing. In systematic listing, you come up with the actual list of possible outcomes of an event. Let us see the next set of examples. For example, number 3, we have Ivan wants to use a 3-digit password for his locker. He wants to use the digits 3, 5, and 6. Use systematic listing to determine all the possible combinations that Ivan can choose from, considering that A, repetition of digits is not allowed, and B, repetition is allowed. For the first condition, the combinations for a 3-digit password would be 3, 3, 5, 6, 3, 6, 5, 5, 3, 6, 5, 6, 3, 6, 3, 5, and 6, 5, 3. Where a digit is not allowed to be repeated, we will only have 6 combinations of 3-digit passwords. We have this 356, 365, 536, 563, 635, and 653. Our next condition is repetition of digits is allowed. I think would be you can list all the possible outcomes starting with 3, then with 5, and lastly with 6. Starting with 3, we have 3, 3, 3, 3, 3, 5, total of 9, where the first digit will start with 3. The next, starting with 5, we have 5, 3, 3, 5, 3, 5, and lastly, where the first digit will start with 6, we have 6, 3, 3, 6, 3, 5, 6. Now, with systematic listing, we have listed all the possible outcomes for combinations of 3-digit passwords having 3, 5, and 6, where the repetitions of digits is allowed. With this, we have shown that there is a total of 27 possible outcomes. And for the first condition, we have a total of 6 possible outcomes. The use of the tree diagram and systematic listing will help us identify accurately all the possible outcomes of an event, while the fundamental principle of counting will help us or enable us to determine the total number of possible outcomes of an event. Again, it only helps us to determine the total number of possible outcomes of an event without giving us the possible or the specific possible outcomes of our event. For fundamental principle of counting, if the ways to do a certain task can be split into R steps, and there are n sub 1, and then there are n sub 1, n sub 2, to n sub R ways of completing the task, ways under these respective steps, then the total number of ways for this task to be completed should be given by n sub 1 times n sub 2 times n sub R. Wait, tama ba sabi ko mga po? Times until n sub R. If the ways to do a task can be split into R steps, and there are n sub 1, n sub 2, n sub 3, to n sub R ways under these respective steps, then the number of ways for that task to be completed should be the product of this n sub 1 to n sub R. In symbols, we have n sub 1, times n sub 2 times n sub 3 until n sub r. This time, let us have the following examples. 4 sub-items under example 4. For the first item, we have a student is choosing between science S or math M as a course of study and intends to enroll in at UP, DLSU, or ADU. With this, in this item, we have two steps included. First is choosing a course of study, and second is choosing a school to enroll in. And for our first step, we have two options, sciences and math. So meaning we have 2, then multiply it to the number of possible options for our second step, which is choosing a school to enroll in. We have 3 options there, UP, DLSU, or IU. And that would be 2 times 3, meaning there would be 6 possible combinations of choosing a course of study and a school to enroll in. We have 6 possible outcomes. For the second item, we have a coin is tossed 3 times. In this equation, we have 3 steps. First is first toss, second step is second toss, and the third step would be our third toss. And for each step, there would be exactly 2 possible outcomes. In tossing a coin, the outcomes could either be a head or a tail. For the first toss, we have 2 outcomes. Second toss, we have still 2 outcomes, head or tail. And for the last toss, we still have 2 outcomes, head or tail. Getting the product of these outcomes, we have 2 times 2, that's 4, times 2, we have 8. Meaning there are 8 possible outcomes for this event where we toss our coin 3 times. Letter C, Ivan wants to use a 3-digit password for his locker. He wants to use the digits 3, 5, and 6, such that repetition of digits is not allowed. Okay? So we have still 3 events here, choosing digits for the first position, then choosing for the second position, and thirdly choosing for the third or last position. And we need to consider our condition where the repetition of digits is not allowed. For our first position, we have 3, 5, and 6, and with those digits available, meaning we have 3 options. For the first position, we have 3 possible digits to choose from. And since we cannot repeat a digit in this password, if we are already able to choose 1 digit among the 3, we will only be left with 2 options for our second digit. Choosing the second digit will give us only 2 options. And lastly, choosing our third digit, since we already have 2 digits for the first and second positions, you're only left with 1 digit or 1 possible digit for the third position. Okay? So multiplying these possible outcomes for each step, we have 3 times 2, that's 6, times 1 equals 6. So 6 possible outcomes. There will be 6 possible 3-digit passwords for this locker where a digit will not be repeated. And letter D, Ivan wants to use a 3-digit password for his locker. He wants to use the digits 3, 5, and 6, such as that repetition of digits is allowed. Now, notice that it's very similar to item C. The only difference is, for item D, repetition of digits is allowed. Meaning, if your first digit is 3 for your password, you can have another, or you can repeat that digit for your password. You can have 335, 333, 333, or so long as a digit will be repeated. For our first position, we have 3 options, either 3, 5, and 6. For our second position, since the digit chosen in the first position will be repeated, we still have 3 options for this position. And lastly, still 3 options for the third position, since the digits in the first and second position will be, or the digits in the first and second position are allowed to be repeated. Getting the product of these possible outcomes, we have 3 times 3 is 9, times 3 equals 27 possible outcomes. So recap, for letter A, we have 6 possible outcomes. Letter B, that's 8 possible outcomes. C, 6 possible outcomes. And for letter D, we have 27 possible outcomes. Now, we have shown that using the fundamental principle of counting may tell us, or may not be able to tell us the specific possible outcomes of an event. However, it will give you an idea of the total number of possible outcomes for such events. Without, of course, drawing your tree diagram or doing a systematic listing for the possible outcomes.